Welcome back. So in the previous video, we've just had a look at Depth-First Search, DFS. So it's a very, very simple algorithm. It's just going to recursively jump as deep, as far downwards as you can along one path, and then it's going to backtrack when necessary. More importantly though, we've just noted that DFS has some critical failures, particularly in the fact that it is neither complete nor optimal, because of the fact that it can, in its downwards trajectory, follow infinite paths essentially, and it can be stuck forever exploring these and never being able to return back up the tree in order to explore some form of like right subtree or something like this to actually find where the goal is instead. So it gets lost in the weeds. So Depth-First Iterative Deepening, DFID, is a really, really interesting augmentation to depth-first search, which is going to actually fix these issues and give us competitive performance. So the main issue before was this idea of unbounded dives, this progression by depth without limits. So all DFID is going to actually do is impose iteratively a series of limits each time the algorithm runs. So what is the search strategy? It's just going to be that we are going to do repeated depth-first searches, except every time we're going to be doing this with an increasing depth limit. Okay, so at the beginning we're going to impose a depth limit of 0, and then 1, and then 2, and then 3, and so forth. So we're going to be iteratively raising the limit that we're allowing search to continue downwards. This is going to create some really interesting behavior and some really interesting time and space complexities. But at the end of the day, like the spoiler alert is, it's a pretty competitive algorithm. So let's try to draw up some example behaviors. Okay, so we've drawn up the example here a little bit different than we have in previous videos because of this idea that we have this iterative version. We have different iterations of the algorithm. So I've drawn up here 3 iterations. Iteration 0 with a limit of 0, iteration 1 with a limit of 1, so forth. So let's have a quick look then at how this progresses. So in the very first iteration of the algorithm, of course, we're going to have the root node, we expand the root node, and we go to generate its children, B and C, as we usually do. However, what's happening here is that we have imposed a depth limit of 0. So what happens is we find both B and C, we go to generate them, but we say, hey, your depth of 1 is greater than our current limit, so we do not generate these children. They are not valid successors of A. So what this means is, in a very silly sense, the very first iteration of the algorithm, you expand the root node, and then we're done. We didn't find the goal. You're often not going to find the goal in the root node, but hey, technically you could. But it's obviously a bit of a dummy step. Let's move on then to the next iteration, iteration 1, where we have a larger limit. So in this case, we do expand A, but we're going to find new children this time, right? So we're generating B and C, and B and C both have a limit of a depth of 1, which is within our limit this time. So this time they are both added to our open list, which is our, if you remember from DFS, it is essentially a last in, first out queue. And so we add in both B and C, but again, the order of which one of those, so it's up to tie breaking, whichever one you decide to put in first, they're ranked the same. Just for consistency, I'm going to put in C, B. Well, B here seemed to be the last one that we put in. So next time we're going to pop and expand B. You would go to generate its children, D and E. However, the children D and E both have a depth of 2, which is exceeding our current limit, so neither of them would be added in. At the next step then, we only have C left, so you'd go to expand C, you'd also expand C, you'd find that its children also exceed the limit, and we would conclude search. So thus far, we have not yet found the goal. We're essentially continually proving as we increase the limit whether or not there is a valid solution to find. As well, I think so far, we haven't really seen the DFS search behavior, right? Because when we get into this limit 2, you'll now start to see that the order that we expand things really is following this DFS. So for limit equals 2, of course, again, we're going to follow the same stuff. So of course, we expand the root node, we find B and C, we're going to add these in, either way. In this situation, hopefully the same, it's C and B. Again, we last in, first out. We're going to pop and expand B. This time we generate its children. So D and E are both valid children. They both have a depth of 2, and so they're within our current limit. We actually find and add them this time. So C remains in the open list, and now we find D and E. You can put them in either order, doesn't matter. However, now this is still where we see that the DFS behavior exists. We're trying to go down as far as we can first. So we actually look at D then to see, hey, can we go further downwards? So even in the case, right, that there were further connections downwards, again, these would now have depths outside of the current limit, and so we would not generate them as valid. And then you would continue through, you'd expand E, you'd find the same thing, you expand C. That actually brings in then, of course, our F and G in either order. I feel like I did G and F last time. Doesn't matter, it's tie breaking. And ta-da, what you see is that we have again traversed the tree in the same idea of DFS, but there's this depth limit happening. So I think then we come back to the idea of, okay, so why was this actually useful? What was the point of it enforcing this depth limit as we're going across? And so I think only then, when we start to get back to discussing the properties of the search algorithm, properties, where again we're going to be looking at our completeness and optimality and our time and space complexity. Now we can start to see that things are looking quite different. Okay, and so in terms of completeness, this essentially was what DFID is all about. By imposing this depth limit, we can essentially fix the critical failure we previously saw, where the length of the longest branch may continue unbounded downwards down some left subtree and would never be able to escape and come back up to find the goal on the other side. Because we're imposing a depth limit each time, essentially at each iteration of the algorithm, we'll always find all nodes of that up to that depth limit. And so that's the exciting part of this. So this algorithm is complete. We've essentially solved this issue. What's maybe a little bit harder to see then is let's talk about optimality. So previously DFS was definitely not optimal because you could find any goal, say there's another goal 2, I'll draw it up. There could be another goal much, 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 much lower down the tree. Depth first search continues downwards, it would find this much deeper goal and it would miss the shallower one that was on the other side of the tree. So in that case, it would not, well, DFS is not optimal. What's really interesting here about this iterative behavior is that actually DFID is optimal with a small asterisk, which we'll talk about. But because we have this depth limit, again, we're expanding all nodes up to the current depth limit. So we will always find the shallowest goal. If there was a shallower goal than this current G, if there was one in depth 1, well, the previous iteration of the algorithm would already have expanded that goal node and returned. And so that's the beauty of enforcing this iterative depth limit. We actually are able to not only find complete solutions, but we can always find the optimal solution this way. So that's quite exciting. Now, I have drawn an asterisk. The asterisk here is involved because of the idea that, again, this only works when the depth of a node is directly related to the cost. So essentially you have some form of uniform cost. All steps are the same such that depth is linearly increasing, right? So essentially cost and depth are directly related. We've seen that in problems with different variable costs. That is where UCS enters the picture, and then we would not have these guarantees of optimality because the depth is not related to the cost as is necessary. And so then we're going to move our attention over to time and space complexity. So these are a little bit more complicated than they were in the past. We're going to have a look at essentially let's do time complexity first. How many nodes are we going to be expanding in the algorithm as a whole, because we have all these iterative versions. So in the very first limit equals 0, we just have 1. extremely boring. You're just expanding the root node and we stop, right? In the next iteration, we're going to expand everything at depth 1 that we've seen before, right? This is essentially equal to b. It's the number of decisions, the branching factor. How many things can you do from the root node each time? The branching factor in this problem is 2, but it's just b generically. What's going to happen then is in the next step, for each of these b things you could have done, they as well can now do another b. So essentially, right, what you're seeing is this is essentially b to the 0, b to the 1, b squared. It's b to the power of what your current depth limit is. So how far does this go? Well, of course, the very last depth limit that you will reach is d, the depth of the solution itself, the shallowest goal node. If similarly to how we've done in the past, again, if we look at these this sum of polynomials, it's the last term that dominates, and so the time complexity is just O of b to the d. And so then we go back to space complexity. So we just saw that for DFS, the space complexity is the branching factor, right? How many nodes per expansion are you going to have to store? Multiplied then by m, which was the length of the largest branch. Well, here, the very last term similarly is going to follow like this, but instead it's just O of b to the d this time. And we've already seen and talked about the idea that m is the full depth of the tree, which is going to be often substantially larger than d. But yeah, so we get a pretty intuitive space complexity here as well. In an exercise video, we are going to do a little bit of a dive into, like, for DFS, what implementation hack is allowing us to get this much smaller space complexity. So stay tuned for that. But otherwise, yeah, for the simple purposes here, we can just say, hey, you're not going to have to retain all the information. You can discard a bunch of things. It's just going to be O of b to the d, and that follows from our O of b to the m. And so this takes us to the end of DFID. But I think what's really interesting about this algorithm, perhaps at first glance, it looks very silly, right? We're doing the same work over and over and over again, right? Like at this iteration, we had to expand A, we had to find B and C, we had to generate them, ta-da. You're going to do that again at this, and then at every single iteration thereafter, you're repeating all of this work that you've already done before. What's actually quite interesting then is I'm going to tell you as the spoiler, the worst case time complexity of DFID is exactly the same, b to the d, as BFS. Why is that the case, right? Because of course BFS is doing similar ideas, but it does not do all this repeated work. And so we'll have an exercise video on that as well. But right, you gotta really start reasoning over how we define these worst cases. And then really what starts to enter into the equation is this real-time performance. But DFID it holds its own. And so I think it's a really interesting algorithm in our stepping stone journey. And it's cool how just a rephrasing of the way we define the problem to add in the step limit can actually shore up some of the main concerns, the main issues we had with depth-first search. So please stay tuned then as we move onwards from, this was the last uninformed search algorithm we'll be looking at, and we'll start exploring the world of heuristic search. So we're going to step into the idea of informed algorithms, which is really a very, very important stepping stone in our search journey. So please join me there as we look at greedy best first search. Thanks.